For the first part of this lecture, we'll be talking about experiments with more than one IV or more than one independent variable. So just to refresh, experiments are those contexts in which researchers manipulate or control certain variables. These variables are called the independent variables, denoted as IVs, and they then examine the effect that these variables have on some measured variable, oftentimes something of interest to the experimenters. And these are often referred to as dependent variables, such that they depend, or their outcomes often depend, on the independent variables. Now, previously we talked about experiments in which there was one independent variable and one dependent variable, right? Like, how does the type of pet that you own impact how much stress you feel? Pet type is the independent variable. The amount of stress a person feels is the dependent variable. Now, a lot of experiments are conducted at this level. That being said, there aren't really any theoretical limits on how many variables a person could include in their experiment. So you could have all different types of independent variables and look at how that impacted stress, for example. So I could have what type of pet a person owned, whether they lived in their own house or an apartment, whether they were tall or short, whether they like to watch baseball or not, and I could just keep throwing in as many of these variables as I wanted, theoretically, and look at how all of them impact stress, along with what their relationships were in how they impact stress, which we'll talk about a bunch more in a second. Now, theoretically, that's totally fine. Practically speaking, that becomes confusing and unwieldy really, really quickly if you have too many variables at play at any given time. Because remember, the whole goal of experiments is to isolate the effect of a few variables on some other variable so that we can begin to examine what their relationship is. This is related to internal validity. Internal validity is much easier to manage in an experiment when you have few independent variables. It becomes difficult to manage when you have many independent variables. And so this would be one of those practical limits. Now, these experiments in which you have multiple independent variables are often referred to as factorial designs or factorial experiments. And here, factorial is just referring to the independent variables themselves, which are often sometimes called factors. Now, we won't talk about it in this lecture. Well, we won't talk about it in this entire semester's worth of talking about it, because this is something that oftentimes only comes up in more advanced statistical classes or certain types of research. And that is when you have experiments or studies in which you have multiple dependent variables at the same time. And these are often referred to as multivariable or multivariate designs or experiments. Of course, you can mix and match, right? You could have a factorial multivariate design in which you have multiple independent variables and multiple dependent variables. Now, there are certain types of cases where it is important to use a multivariate design, but that again kind of goes outside the scope of this class. A good example of that would be, so we know from previous literature that people's anxiety and their depression are highly related. So oftentimes when measuring these, we measure both of them at the same time, and then of course look at their relationship to each other. So I could look at pet ownership, what type of pet you own, as the independent variable, and look at how that impacts both stress and anxiety, or excuse me, anxiety and depression. And so I could then have one independent variable and looking at how it impacts two dependent variables. Now, you could sit there and say, well, I could have just run multiple experiments, and sometimes it is actually easier to run multiple experiments, though there are certain benefits that you can reap when you run experiments that have multiple independent variables and multiple dependent variables. This little note about practical limits versus mathematics. So this is kind of what I talked about earlier, of there isn't really a theoretical limit, right? You could throw as many independent variables as you want, and as long as you could get enough people to get all the conditions satisfied, you could pump all that data into a computer, and it will be able to run the standard statistical tests for those types of situations without any problem. It will pump out the numbers and it will give you all of that data. Now, on an interpretation side, that becomes pretty difficult, because mathematically the computers and the models don't care how many variables are thrown at it, for it is just actually complex multi-dimensional space, not like space outside, but mathematical space. And these models are indifferent to how many dimensions of that space exist. But chances are already you're thinking to yourself, well, what the hell are these dimensions that you're talking about? That's not really the most important here. It's just that know that there's this fine line between too many variables in your experiment and sometimes having too few. Okay. Why would you run an experiment with two independent variables when you could run just two separate experiments, especially if it would be easier to manage internal validity with less independent variables? And the reason for that is you can see more in an experiment that has two variables at the same time than you could have if you had just run those as separate experiments. And the reason for that is because different independent variables can influence one another and look at or change how they impact the dependent variable. And so when this happens, we call these interactions, which is actually an appropriate name, I think. And that just refers to how a set of independent variables influence one another and thus impact their relationship on dependent variables. So here's just sort of an intuitive example from your textbook to have that fit in your mind, hopefully. So here, the dependent variable is how much people like certain types of food. That is shown here on this axis, where as you go higher and higher, people's liking is increased. And so the higher someone scores or a group scores, the more they like some food, and the lower it is, the less they like it. The two foods that they're considering in this case are ice cream and pancakes. Right? So we're looking at how much people like ice cream and how much they like pancakes. And so overall, you could just do it like that. That would just be one study where you get a bunch of people and you're like, okay, how much do you guys like ice cream? And how much do you like pancakes? And you're like, okay, people like pancakes more than ice cream, or vice versa. Now, these two colored lines here, the green one going down and the orange one going up. Sorry if you're red-green colorblind and that is difficult for you to see. But the hot line is this one going up and the cold line is this one going down. So you could have just, again, looked at people and been like, okay, we're going to give you some cold food. How much do you like it? We're going to give you some hot food. And how much do you like it? You could have done that also. But now the magic of having IV or multiple independent variables is you can look at how they interact with each other. And that you can see with the way that this line is crossing over. Such that for ice cream, people don't really like it when it's hot, right? But they do like it when it's cold. And the opposite pattern is true for pancakes. Most people don't really like pancakes that much when they're cold, but they like them a lot when they're hot. Now, you would never have been able to see this if you didn't have both of those independent variables in the study together. Because otherwise you would just be knowing about how much people like ice cream and pancakes, and they've just been like, okay, yeah, I like these things. And how much do you like food hot and cold? Well, on average, I like hot food more than cold food. And there you go. But in real life, it is much more nuanced, right? It depends on what type of food I'm eating and what temperature that food is. And so by running experiments that have multiple independent variables, we are able to examine these type of contexts, which for a lot of research purposes is greatly beneficial. All right, so as mentioned previously, when you have multiple independent variables, these are referred to as factorial designs, where each independent variable is referred to as a factor. Now, each factor will oftentimes have levels. The levels are the different conditions that are possible in the independent variable itself. So for the previous example that we talked about on that last slide, between the types of food you were examining, ice cream and pancakes, here type of food would be the independent variable, and pancakes was one level and ice cream is another level. Now, cells are kind of like the smallest boxes you could form when you look at all the possible ways that you'll have to sort your participants. And that just refers to all the ways you can cross your independent variables and make various little combination squares. Hopefully with the examples that will make a little bit more sense. So for this first example, let's say we're just examining something about how happy people are in general, or children, let's say, is what we're interested in, so that would be our dependent variable, and we have children who either play games or don't play games, and we have also children who run track or do not run track. And so here we would have a factorial design because we have video games and track as our independent variables. So we would say we have two factors. Each of these factors has two levels, right? So the games factor, people either play video games or they don't, right? There are two levels there. And we have children who either run track or do not run track. And so again, we have two levels. And so this leads to a total of 4 cells. What are these 4 cells? Well, I have people who play video games and run track. I have people who play video games and do not run track. I have people who do not play video games and do run track. And then I have people who do not play video games and also do not run track. And so in this way, I have each of the possible pairings of levels that I could have, and that leads me to these 4 cells. This type of study would often be called a 2x2 factorial design, where the 2 and 2 are just the number of levels in each of the various IVs that are present in this study. So another one of this would be, again, let's say we're just looking at how happy people are. And this time we're interested in how the type of games people play and the type of food that they prefer impact how happy they are. And so in game type, we have people who play electronic games, people who play board games, or people who play athletic games. And in food preference, we're interested in whether people like savory food more or whether they like sweet food more. So here again, we have 2 factors, right? Game type and food preference are the independent variables or the factors. The first one, game type, has 3 levels: electronic games, board games, and athletic games. And the second one has 2 factors, where it's savory or sweet food. This would be why this would be called a 3x2 factorial design. If you had switched your IVs when you were talking about it, you could call it a 2x3 design. That's totally fine, and that doesn't really change anything meaningful. Now, here they would be a total of 6 cells, because now I have people who play electronic games like sweet food, electronic games, savory food, board games, sweet food, board games, savory food, athletic games, sweet food, athletic games, savory food, right? All the possible ways that I could combine that. So this is also one of the reasons where you could see that if you have too many independent variables, the number of cells that you have increases really, really quickly, and that will increase the number of participants you need in order to have adequately powered studies, and that can get out of hand really, really fast. Because just using IVs with 2 levels, if I have 2 factors, each with 2 levels, that's 4 cells. If I have 3 independent variables, each with 2 levels, that's 8 cells. If I had 4, that would be 16 cells. If I had 5, that becomes 32 cells. And now, if I have to have 50 people in each cell to have an adequately powered study, I'm going to need hundreds and hundreds of individuals in my studies, and it will make interpretation more difficult. If you have many levels per independent variable, it can get even more crazy really, really fast. So another advantage of factorial designs is they allow us to examine or empirically test for moderators. Moderators are just variables that, depending on their level, modify the relationship between 2 other variables. Oftentimes another independent variable in the study and the dependent variable of interest. Now, these are tested for using interactions, because ultimately an interaction is just showing that 2 independent variables interact in complex ways in their relationship with the dependent variable, and a lot of times that is a hint showing that there is some type of moderator present. This same type of evaluation is an effective way to study or evaluate external validity of specific types of variables. So let's say, hypothetically, I was interested in how much people subscribed to a just world phenomena based on their socioeconomic class. So just world phenomena is this idea that ultimately the world is a just place and things happen for a reason. And I want to know now how much people's socioeconomic background influences how much they believe in the fact that the world is a just place. Now, I might say to myself that people who are high in socioeconomic status think that the world is just, and people who are very low in it don't think it's just. But now, if I did that study in the United States of America, great, sure, I could find that effect, maybe, let's see, but that doesn't necessarily mean that I'm going to see the same effects in India or in Japan or in Sudan or in Russia, for example. And so what I could do now is take people from each of those different countries, use their nationality as one independent variable, their socioeconomic class as a second independent variable and then measure how much they likely subscribe to this just world phenomenon. And now what I can do is see, do the various people from different countries all have the same relationship when it comes to their socioeconomic class and how much they believe in the just world phenomenon? Or are there different relationships between the socioeconomic class and how much they believe in the just world phenomena based on their nationality? If those relationships changed based on nationality, we would say that nationality moderates the relationship between socioeconomic status and how much people subscribe to beliefs in a just world. In that case, nationality would be the moderator. When that moderator is something like nationality, then that would be a sign that that study we originally did in the United States does not have very high external validity because that relationship is different in different nations. Just a note, things like age and culture are oftentimes referred to as participant variables, even though they're used as independent variables, but since they can't be manipulated, they're not true independent variables. But we do use them as they are, as if they're sort of quasi-independent variables would be another way of thinking about it. Just because we can't actually ethically manipulate them, but we oftentimes use them as categorizations in our experiments. Okay, some terms. A lot of times when dealing with factorial designs, you're going to hear things like main effects and interactions. So we already talked about interactions. Interactions are just how our independent variables influence one another in their relationship to the dependent variable. But just because we run factorial designs and we look at those interactions doesn't mean we cannot also examine how each single independent variable individually contributes to changes in the dependent variable. And these are referred to as main effects. So in a factorial design, you're always going to have main effects and interactions. The interactions are how the independent variables influence one another in their impact on the dependent variable, and the main effect is the overall contribution of each independent variable separately on the dependent variable itself. Now, it's funny that they're called main effects because almost always when there are significant interactions, people tend to focus on those more. Also, the more independent variables you have in a design, the more types of interactions you're going to have. So if I have two independent variables, I will have two main effects, possibly, one from the first, one from the second, and an interaction between the first and the second. Now, if I was to have three independent variables, however, I have the possibility for there to be three main effects, right? Main effect A, main effect B, main effect C. But now I can also have a whole bunch of interactions. So I can have a three-order interaction, that is how do A, B, and C all interact together. I could have then also three two-way interactions, which is the interaction of A and B, the interaction of B and C, and the interaction of A and C. And so again, this can become really complicated really, really quickly. And when you have very high order interactions, like fourth and fifth order interactions, it becomes very difficult to, well, really talk about it and understand it at a practical level. And that once again goes all the way to the comments I made in the beginning of theoretically and mathematically, you can totally do it. Practically speaking, it gets confusing and complicated really, really quickly. Okay, for the rest of the lecture, I think there are like 8 slides. We're just going to go through some examples to show when main effects are present and when they're not, and when interactions are present and when they're not, and just sort of how those combinations can be present. So all of these, you can find a big table in your textbook in the middle of the chapter somewhere, and they represent a hypothetical study that is a 2x2 factorial design. And what all of these are going to do is it's the same study setup, but as if the results just kept coming out differently, or we lived in 8 parallel universes and different things happened in all of those, even though we ran the same study. Okay, the first factor is age. There are 2 levels, so older people and younger people. The second independent variable is phone usage while these people are driving, and so there are 2 levels again, so people are either on their phone or they're not on their phone. this combination of two independent variables, each with two levels, leads to 4 cells. Older people using a phone while driving, older people not using a phone while driving, younger people using a phone while driving, and younger people not using a phone while driving. The dependent variable here is the number of accidents these people get into in a driving simulator. And that will ultimately then just be evaluated. Okay, so the first one. So here what we have is, we'll start here in this middle of the table and kind of how to read this. So I have younger drivers and older drivers, whether they're on their phone or not. So younger drivers, when they're on their phone, get into about 10 accidents, but younger drivers, when they're not on their phone, only get into 4 accidents. Older drivers, when they're on the phone, only get into 4 accidents, and not on the phone, they get into 10. Now, here you can see, or just once you're, I guess, familiar with these, just looking at these cells, you'll be able to say that yes, there's probably an interaction. It is easier to see it on this graph where you see the presence of non-parallel lines. These lines that are crossing over, sometimes this is referred to as a crossover interaction, but for the most part, you only really care about interactions happening and not, and then how to talk about them. But you'll get a lot of that information in a statistics class where you study ANOVAs or multivariate regression. Okay, so here's just a copy or another way of representing what is in these medium 4 cells, right? So the lighter blue line is the older people, the darker one is the younger drivers. So younger drivers on the phone, 10 accidents, right? That's right there. And then younger drivers not on the phone, only about 4 accidents. That's right there. So this switch of how age and phone usage change how people have accidents, right? So we're seeing that younger drivers have more accidents when they're on their phones than not, but the opposite pattern is true for older drivers. Again, a way of signifying an interaction. However, in this case, there are no main effects. What do I mean by this? When I'm talking about no main effects, I mean the overall number of accidents is the same for younger drivers and older drivers. We can see that right here in these two blues over here. If I was to take the average accidents that younger drivers have, right, 10 plus 4 divided by 2, that gives me 7. That's where that 7 is coming from. Same thing over here. So since the overall number of accidents is not different for younger and older people, we would say there is no main effect of age. That age doesn't seem to change how many accidents people have. In this case, the same is true for phone usage. There is no main effect here for using your phone on accidents, right? Because people on their phone have about the same amount of accidents as people not on their phone, right? So here is one of those places where you can see that they all don't need to come together, right? So this is an example of no main effects whatsoever, but one interaction. On to the next one. Okay, so here, just looking at the graph directly, you can see that there's 2 parallel lines. When you have lines that are parallel, that is a good sign that there is no interaction, because there is some difference in some type of grouping, but the relationship of the groups is still the same. And so here what we can see is there is a main effect of age, right? Younger drivers get into more accidents than older drivers, but there is no main effect of cell phone usage, because whether you're on your cell phone or not on your cell phone, people have on average about the same number of accidents. Now, the relationship is the same. There's no cross pattern or no spreading pattern. Again, no interaction, but one main effect and no other main effect. Now, again, please note, this is sort of a loose way to give you an interpretation, not even an interpretation. It's sort of just like an intuition about when you have main effects and when you don't, and the different ways it can combine. Unless you run an actual statistical model with some type of probability test and then look at that to know whether these are present or not, it's not enough to just look at some data and be like, I think there is an interaction. You would actually have to run the stats behind this. This is just a way of showing you what these possibilities could look like. Okay, here's another one where we again have one main effect and no interaction. So no interaction easily seen here because the 2 lines are parallel. Technically, they're almost on top of each other, but that still fits as basically parallel lines. So here I can see that age is not a main effect this time, right? Younger drivers and older drivers have about the same number of accidents. People on cell phones have way more accidents than not on cell phones. So in this case, being on a cell phone is a main effect. The way it changes for each, right? Younger and older drivers both have more accidents when they're on their phone than not, is the presence, or that shows that there is no interaction. Because using your cell phone impacts younger drivers the same way as it does older drivers. Thus, cell phone use and age do not interact in this case. Okay, here's a more fun one. Here we have significance of all things. Well, okay, maybe not that far, but we have two main effects and one interaction. So interaction again can be seen here because of the non-parallel lines. It's an easier way to see that. You could also see this as the relationship is different. Younger drivers don't seem to change whether they're on their phone or not, but older drivers do change when they're on their phone and not, right? So the relationship of using your phone is different when you're young versus you're old. That is a sign of an interaction again. The main effects here can be seen by looking at these n columns, which are referred to as marginal means. And here you see that younger drivers tend to have more accidents on average than older drivers, so a main effect of age on accidents. You also see that when you're on your cell phone, people have more accidents than when they're not on their phone, showing again a main effect also of being on your phone. So here would be an example where you have all three of those things are significant. Okay, here's another one where we again have all three things, where we have two main effects and our interaction. So again, you can see that even though they're somewhat closer this time, these are still non-parallel lines, which shows that the relationship of these two is different, right? Because oftentimes when we talk about relationships in stats or research methodology, we're really talking about line functions that relate multiple variables, right? This is probably one of the reasons why when you're learning algebra, you get that y is equal to mx plus b beaten into you. This is one of the places where it's actually used, but even here, we don't really talk about it in that term, again, until you were to go and study regression. Okay, anyway, you can see again a main effect, right? Older people tend to have more accidents than younger people in this context. Also, we have people who are on their phone have way more accidents than when they're not. So this is showing a main effect of being on your phone. But now you can also see that the relationship changes differently. When younger drivers go from not being on their phone to on their phone, there is an increase in accidents of about 6 extra accidents when they're on their phone versus not. That, for older drivers, increase is even greater. They go from 3 accidents when they're not on their phone all the way to 12 accidents when they are. So for young people, being on your phone only increased it by 6 accidents on average, whereas for older drivers, it was increased by 9 accidents, right? So the way in which both of those variables combined to impact the number of accidents changes ultimately the way it, maybe that's not the best way of saying it. Okay, another way of saying this would be that age moderates the impact of cell phone usage on number of accidents, right? So we know that being on your cell phone makes you have more accidents than not, but this is even more pronounced for older drivers than it is for younger drivers. So here, age is moderating cell phone use on the number of accidents. Okay, yet another one. Here we have no effects in at all, right? This would be a study that has null findings. So there's no main effect of age, right? Old people and young people have the same number of accidents. No main effect of cell phone use. People who are on their phone have the same number of accidents as not on their phone. There's also no interaction because here all of our cells are the same. So there's really no difference across. The relationship is not changing whatsoever. Again, here you can see that they're parallel lines. They're basically on top of each other, but nonetheless parallel lines. So another indication that there is no interaction. Yet another one. Okay, here what I can see is that I have no main effect of age, right? So both younger and older drivers get into an average of 5 accidents. I do have a main effect for cell phone use, where people on their cell phones have more accidents than when they're not, and an interaction, right? So here again, the way age and cell phone use change the number of accidents. So younger drivers them being on their phones or not doesn't seem to make a difference of how many accidents they have, right? That doesn't change. But for older drivers, it does make a difference on the number of accidents. They, when they're not on their phone, make very few, but when they're on their phones, make many. And so here's just a visual representation, right? For young people, it's not changing, and for older people, it is changing. Again, you see these crossover lines, a good sign that there is an interaction. Finally, here we can see sort of a reversal, but in another way, the same type of thing we talked about in the last one, where we have no main effect this time of cell phone usage, right? People on their phone versus not have about the same number of accidents, but there is a main effect of age, where younger drivers have more accidents than older drivers. Now, the relationship is also different here. Everybody seems to have about the same number of accidents when they're not on their phone, but when younger people are on their phone, they have more accidents. And when older people are on their phone, they have less accidents. And so here, again, age is changing the impact that cell phone usage has on people's accidents. You could, I guess, say that cell phone use changes the impact that age has on the number of accidents. That would be fine too. And a lot of times when we're talking about this, the way in which you will speak about it just reflects your interest as a researcher and the claims that you're trying to make. But there's not really technically a right way or a wrong way when you're just ordering two different variables, even though sometimes it will make much more sense to have one type of order and other times not so much. Yeah. I guess just as an extra piece, so we often use these tables. It's easy to show, same thing with these types of graphs. When we're looking at two-factor designs, it becomes a little bit more complicated when we have three-factor designs, because ultimately then what you would need is two tables like this. Because let's say I also wanted to know about whether this was taking place in an urban area or a rural area as my third factor. And so what I would do is I would look at, okay, younger and older drivers and how they use their cell phones in a rural area, and then I would make a whole nother table exactly like this, except for an urban area. And so again, you can just see that visually it becomes very difficult very quickly to represent higher order factorial designs. But as you get familiar with these, chances are you won't really have to draw them out much like this, and you'll just run a statistical test and look at the outcome of that. All right.